we'd like to continue working with linear homogeneous recurrence relations. We're going to do some more examples where the roots are distinct. The roots of the characteristic equation are distinct. So here we have an is equal to 5, an minus 1, plus 2, an minus 2, plus 24, an minus 3, for n greater than or equal to 3. And we got three initial conditions. A0 is 5, A1 is negative 8, A2 is 50. So the first thing we want to do is write down our auxiliary equation here. I'll put that in red, our characteristic equation. So we have a degree 3 situation. Why a degree 3 situation? Well, here, so it starts at n, right, and it counts down to n minus 3. So there's a space of 3 for the number of terms here. So n minus 3, so degree 3. So we're going to write a characteristic equation is going to be a polynomial of degree 3. So we're going to start off with r cubed. So basically, in place of the an, I'm putting an r, and so see the sub n right here, the sub n, a sub n. So imagine plugging a 3 there, and rather than making it a subscript, make it an exponent. You're going to have what? Minus 5, so equals minus 5. In place of a sub n minus 1, you're going to put an r. Then for an exponent, so imagine you actually plug in a 3 in place of that n, so you got 3 minus 1 is 2. You're going to make that an exponent rather than a subscript. And you just go down, right? Plus 2. In place of an minus 2, I'm going to put an r. And let's imagine in place of that n, I were to put a 3. You'd have what? 3 minus 1 is a 1 power. So you got 2r to the 1 power, right? And then I have what? Plus 24. In place of the a sub n minus 3, I'm going to put an r. And if I plugged a 3 in for the n, I have 3 minus 3 would be the 0 power. That's going to be an exponent rather than a subscript. So we really have what? R cubed equals 5 minus r squared plus 2r plus 24 in actuality. Now this is called a degree 3 polynomial, which we want to get everything on one side and 0 on the right side. So I'm going to have what? R cubed. This will write. It's not writing. We're going to add 5r squared to both sides. Subtract 2r from both sides. Subtract 24 from both sides. And that's equal to 0. Now, it's not clear here what to do next as far as factoring, maybe. So if you look carefully, it doesn't seem as though there's a grouping thing that we can do, a factoring by grouping type thing. It doesn't seem like that's going to work. Doesn't seem that way. So what we're going to do, we're going to see, okay, is there a root that we can find? Now this is something you may have done in pre-calculus back in high school. Actually, we do this in our pre-calculus 1 class here, Tennessee Wesleyan. So possible rational roots, so roots that are fractions, rational roots. So these are possible rational roots. So what we do, we take out the last number, minus 24, and we think of all the divisors of 24. We call these p. So what are the divisors of 24? Plus minus 1. I'm going to run out of space, aren't I? Let me give myself a little bit more space here. So the divisor, so p consists of the divisors of 24, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 8. What else? Plus or minus 12, plus or minus 24. These are all the divisors of 24. So those are my p's. And then my q's are going to be my divisors of the coefficient in front of the largest term. So the largest term, the term with the greatest degree, or the greatest power, is r cubed, and the coefficient there is 1. So the divisors of 1 are plus or minus 1. So if you want all your rational roots are just your p's over your q's. Use a purple for that. My p's over my q's. It's not working. It's really, there it goes, p over q. So if I take the p's and divide by the q's, we're taking each of those blue numbers and we're dividing by plus or minus 1. We're just going to get back those blue numbers, right? Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 8, plus or minus 12, plus or minus 24. Yeah, so really I didn't need to even bother dividing out the q because the q is just plus or minus 1. So these are possible rational roots. So if we have any rational roots, that's roots that are fractions or integers, then one of these has to be a root. So why don't we try, for example, we could try plugging in 1 to see if it works. So we're going to try r equals 1. See if that is in fact a root. So what we could do, we could plug 1 in and see what happens. So we get 1 cubed plus 5 times 1 squared minus 2 times 1 minus 24, and see if we get 0. Do we get 0 is the question. Let's say we got 1 plus 5 minus 2 minus 24. That's equal to what? 6 minus 2 is 4. We got 4 minus 24 minus 20. So this is not 0. So 1 is not a root. R equals 1 is not a root. So maybe try something else. So let's try r equals 2. See if 2 is a root to that equation. So we're actually going to plug in 2 and see if we get out 0 at the end. We're going to do a blank cubed plus 5 blank squared minus 2 times blank minus 24. See if we get 0. So I'm going to plug in 2 for my r. We're going to get, what, 8 plus, what's 5 times 4? 20 minus 2 times 2 is 4 minus 24. Now here we got, what, this is 28. This is minus 28. That's going to 0 out, so we're going to get 0. So yeah, r equals 2. R equals 2 is a root. So r equals 2 is a root. We found a root. So I'm going to write r equals 2 is a root of our polynomial. Let's write what our polynomial was. R cubed plus 5r squared minus 2r minus 24 equals 0. Let's see if I can remember that. Let's see. R cubed plus 5r squared minus 2r minus 24 equals 0. Is that right? Let me check. Let me just double check. Yep, that's right. All right, so we got one root. So because r equals 2 is a root, that means r minus 2 is going to be a factor of that polynomial r cubed plus 5r squared minus 2r minus 24. So r minus 2 is a factor of just the polynomial, not the equation, but just the polynomial. So what we're going to do now, we're going to do long division to find additional factors. Hopefully you've seen long division before. It's something that you do a lot, oftentimes in a pre-calculus course in high school, sometimes Algebra 2 in high school. We actually do it in our pre-calculus 1 course here at Tennessee Wesleyan. So I'm going to take r cubed plus 5r squared minus 2r minus 24. I'm going to divide that by r minus 2. And now I'm going to ask the question, how many times does this r, how many times do you have to multiply that? Or what do you have to multiply that blue r by to get this r cubed right here? Well, r squared, right? I have to multiply this blue r by r squared to get r cubed. So I'm going to write a r squared here in the square column. I'm going to call this the square column, or the square zone. So now let's do that. Let's take r squared times r is going to be r cubed. And then I'm going to take r squared times this -2 right here. So r squared times that -2 is going to give me -2 r squared. So now what we have to do, we actually have to do a little subtraction. So imagine you got a subtraction. I'm going to put a purple subtraction sign right there. Some people don't do that. I'm going to go ahead and do it. So we have what? R cubed minus an r cubed. That's going to zero out. And we're going to have what? 5 r squared minus -2r squared. That's going to be the same thing as adding 2r squared, right? So we're actually going to have what? 7r squared here. Yeah, so imagine that negative distributes, right? That negative here out front distributes, and we'll make it a positive 2r squared. So you got 5r squared plus 2r squared, 7r squared. All right, then I'm going to bring down this -2r. And now I'm going to ask the all-important question, This r right here out in front, what do I have to multiply that r by to get this 7r squared right here? Well, I got to multiply that by a positive 7r, right? So I'm going to do that. I'm going to do this positive 7r times this r out in front. It's going to give me 7r squared. I'm going to take this 7r times -2. It's going to give me a -14r. And I'm going to subtract these doodads. Now, a lot of people don't bother putting that subtraction in the parentheses. I'm going to do it. Keeps me straight, maybe. So I'm going to take, what, 7r squared minus 7r. That's going to zero out. We're going to take this red right here. I'm going to do it green. And we're going to take -2r right here, right? -2r minus a -14r. Now, if you think about this minus out front and this minus here in front of the 14r, that's going to be a plus, right? Double negative makes a plus. So we're going to actually have -2r plus 14r. -2r plus 14r is going to give me 12r. So I got 12r, and now I'm going to bring down -24 there. Let's write it correctly. Come on, dude. Dude, turn red. Thank you. -24. Bring down my -24. Now I'm going to ask the all-important question. This r here out front that I'm doing in green, what do I have to multiply that r by to get the 12r down in green? Well, I got to multiply by a 12. So I'm going to put a plus 12 here above the constant, -24. So I'm going to put a plus 12. So what's plus 12 times r out front? Well, 12 times r is 12r, so I'm going to write a 12r down below. I'm going to take that positive 12, and I'm going to multiply it by the -2 now out in front there. 12 times -2 is going to be -24. And now we're going to subtract these doodads. Subtract and put a little parentheses there. Those just cancel, so you get a remainder of 0. Yeah, remainder of 0. So basically what that tells us the factorization for r cubed plus 5r squared minus 2r minus 24. So what do we have? We had what? R cubed plus 5r squared minus 2r minus 24. That was a polynomial. And it was set equal to 0, right? We had an equation. So that factors into r minus 2, right? That was one of our factors that we got from the root earlier, r equals 2. And then we're left with what? R squared plus 7r plus 12. That's the quotient. That's the quotient up top there, and that's equal to 0. So what we have a linear term, r minus 2, and we have a quadratic term, r squared plus 7r plus 12. So now we can factor the quadratic term. Come on, right? R minus 2 stays, and the quadratic term, we're going to make what? Factor it. We're going to make 2 pairs of parentheses and equals 0. So first of all, I'm going to put a r in the first parentheses, a r in the second parentheses, and then I got to find two numbers that multiply to give me positive 12 and add to give me 7. So I'm going to do a positive 4, a positive 3, right? Positive 4, positive 3, multiply to give me 12, they add to give me 7. So now I have three factors, and I'm going to set each factor equal to 0 by the zero product property or zero factor property. And that's going to give me three distinct solutions here. We're going to have r equals 2. That's one of our solutions. Hey, we already knew that from earlier. R equals negative 3. Oh, we got a new one. R equals negative 4. We got a new one. So here are our three distinct solutions. So we had a degree 3 recurrence relation, and we have three distinct solutions. So now we want to come up with the form for the solution, When you have a linear homogeneous recurrence relation with distinct roots, remember the form is going to be a sub n. That's going to be your solution sequence, your closed form of your sequence. It's going to be a linear combination of geometrics. So you're going to have alpha 1 times 2, that's your first root to the n, plus alpha 2 times negative 3, your second root to the n, plus alpha 3 times negative 4, your third root to the n power. Okay, so that's the form for your solution, your closed form of your sequence. So all we have to do now is just solve for alpha 1, alpha 2, and alpha 3. So that's what we want to do next. We're going to, let's go green. Find alpha 1, alpha 2, alpha 3. So I totally forgot what my initial conditions were. A0, A1, A2. They were way back at the beginning of the problem. Let me go back. A lot of work, right? A lot of work. So here they are. Here are my initial conditions. A0 is 5, A1 is negative 8, A2 is 50. 5, negative 8, and 50. Let's see if I can remember that. 5, negative 8, and 50. 5, negative 8, and 50. 5, negative 8, and 50. All right, so for A0, that just means we're plugging in a 0. And for n in the form, so we're going to have something like alpha 1. So we're going to have what? Times 2 to the 0 plus alpha 2 times negative 3 to the 0 plus, squeeze this in, alpha 3 times, can I squeeze in a 3 there, times negative 4 to the 0. And I kind of ran out of space. That was a 5. Okay, equals, that was, what was that, 5? Yeah, 5. I'm going to back this up. This was a negative 8. Run out of space. And this is going to be a 50, right? All right, so we plugged in zeros for n. Now we're going to plug in a 1, right? So we're going to have an alpha 1 times 2 to the 1 plus alpha 2 times negative 3 to the 1 plus alpha 3 times what? Negative 4 to the 1. And then on the bottom one, we're going to plug in 2's for n, right? We're going to have alpha 1 times 2 to the 2 plus alpha 2, negative 3 to the 2 plus alpha 3 times negative 4 to the 2. So you're going to come up with 3 equations and 3 variables. Let's see if we can write these out nicely. We're going to have what? Alpha 1 plus alpha 2 plus alpha 3 equals 5. First equation. Second equation is going to be what? 2 alpha 2 minus 3 alpha 2 minus 4 alpha 3 equals negative 8. And the last equation is going to be what? 4 alpha 2, what? Plus 9 alpha 2, what? Plus 16 alpha 3 equals 50. Now, the easy way to do this, to solve this system of linear equations, is to do a matrix where for the alpha 1 coefficients, we're going to put 1, 2, 4. And for the alpha 2 coefficients, we're going to do 1, -3, 9. And for the alpha 3 coefficients, 1, -4, 16. And then a bar. Then on the right-hand side, 5, -8, 50. This is actually an augmented matrix. Let me write this augmented matrix. It's a matrix that represents this linear system. And what we're going to do, we're going to row reduce this. So I'm going to do an RREF. So you can put that into a calculator. Let's see, I put this into a calculator earlier. And let's see, what did I get here? Let me see what I got. I can't find it. What did I get here? I didn't do anything. I didn't put it in. Okay. Don't think I put it in. Did I put it in? It'd be really fantastic if I put it in. No. Don't think so. Okay. I guess it's time to put it in. Second matrix. Edit. We're going to be doing a 3 by 4. 34 by 4. No, thank you. Three by 4. And we're going to do what? 1, 2, 4 down the first column. 1, -3. 9 down the second column. 1, -4. 16 down the third column. And 5, -8. 50 down the far right column. All right, I'm going to second matrix, math, RREF. Second matrix, enter, enter, and I got, looks like I got, let's see, 1, 0, 0, 0, 1, 0, 0, 0, 1, and, oh, I got some decimals. I got math fraction. Looks like I got 9/5, 6/5, and 2. And those are my coefficients, my alpha 1, my alpha 2, alpha 3 respectively. So I'll plug those back into the form. Okay, so let me get rid of that. Come on, right, buddy. Alpha 1 is going to be 9/5. Alpha 2 is going to be 6/5. Alpha 3 is going to be 2. So I'm going to go back and I'm going to plug them in here. Alpha 1, alpha 2, alpha 3. So this will be actually my solution. Where am I going to put my solution? I'll put it at the very end. Come on, dude. So here's my final actual solution. Forgot what alpha 1, alpha 2, and alpha 3 is. So alpha 1 is 9/5. Okay, so we're going to have a sub n is alpha 1, 9/5 times, what did we have next? Was it 2? Yeah, it was 2 to the n. Plus alpha 2, 6/5 times -3 to the n, plus alpha 3, 2 times -4 to the n. There we have it. There is our actual solution.